Rayleigh-Benard convection. Are you there, please?
Yeah. I'm just sharing the screen.
Okay. Yes. Please. Okay, you have let's say 15 minutes plus 5 for the questions. At 15 minutes, I will give you a hint to go to the conclusions.
Okay.
Please,
Am I
the floor is
visible
yours.
and audible? The screen.
That's perfect.
Okay.
That's perfect.
So just a question. I think I was supposed to be chairman for this session. It's changed.
Yeah. Please. I'm sorry. Just because I'm out of time. I'm sorry for this. Sorry.
Okay. So,
I don't mean to intrude. Sorry.
No problem. But just to be sure that I'm not supposed to be somewhere else. So okay, I'll take over. So
No. Thanks, patience. Thanks, and sorry again.
Oh, go ahead.
Okay, so hello everyone, welcome to this talk. I'm not Dr. Agasthya, actually. I'm still doing my PhD. So this is the work that is still ongoing, and we are doing with this. These are my collaborators with Professor Biferale, Professor Toski, Dr. Patricio Clark, Professor Erhard, and Professor Bartel. And today we will look at the technique of nudging and an application to the when we look at only the temperature field of the Rayleigh-Benard convection. So I will just quickly motivate the system, and the Rayleigh-Benard, the natural convection system is well known. It's a thermally driven flow. But what we want to know is that is it possible to with this nudging, which I will explain what it is later. How can we reconstruct this flow, and in particular to optimize the quality and quantity of information? How much information, in what manner we can collect, and how we can do this. This is the broad idea of this. Of this study, and a very quick introduction to the Rayleigh-Benard system. It's of course driven by buoyancy, and these are the non-dimensional parameters. I will not spend too much time on this because I believe it has been discussed quite a few times before. I will just stress here that here we have the average temperature profiles of the Rayleigh-Benard convection in different states. So when we are well below the critical Rayleigh number, we have we have just a conductive solution. Here, with just with just the average temperature profile, we can have an idea of what the flow looks like with these rolls, and these are well studied. But once we go into a more turbulent regime at higher Rayleigh numbers, with just knowledge of this mean profile, it is impossible. We cannot imagine what the flow will look like just by looking at this, unlike the previous cases. So this is a kind of provocation to go into these kind of things. And what is the Nusselt number? It gives us the ratio of convective heat transfer to the conductive heat transfer, and it's a constant across the domain along in the vertical direction. In a long time average, of course, it's a very chaotic measure. So a quick introduction to what we mean by this data assimilation, but maybe if you attended Professor Biferale's plenary talk on the first day, you know that we have a small amounts of data only in some patches or in some regions. And the main idea is, can we get back this original reference field using the nudged field? Using this nudging field. That is, we have only some data. Can we recover this? And so, what in this study, what we are doing is we are. Sorry, is my cursor visible when I point it? Okay.
Yes, it is.
Okay. Great. Okay, great. So we have this alpha, which sets the nudging strength, and we have information from the reference flow, which we are trying to reconstruct. And so in a new simulation, taking this reference data, we try to reconstruct the original reference flow. And this nudging term, it is a kind of a spring. It's a relaxation term which gently pushes the flow towards this the temperature field towards the reference temperature field. That's why we say it that's why the name nudging is it's very indicative, and that's why we say we try to gently convince this numerical flow. And so we have two types of nudging that we do here. So the first is in our reference field we have some number of probes which measure the temperature, and the first is the Eulerian nudging, where we have these probes which are fixed in the we are working only in 2D here, and we have these probes which are fixed in space, and they collect the temperature over time from these fixed regions. So to construct this this nudging field, we take the temperature of the particle, whatever is the reading, and then in a small box around it with length L, we set uniformly the temperature of the particle for the nudging. And we have the Lagrangian nudging scheme, where we do the same, but this time the probes with which we measure the temperature, these are actually tracer particles. So they follow the flow and again give us measurements along these tracer trajectories. So why is this something worth looking at, or why it is so interesting? Well, because in the past decade or so, this maybe even a little longer actually. So this nudging with in general data assimilation, and especially the nudging technique with velocity has proved to be quite successful. But with thermal flows, it is not so straightforward, because you have this kind of a coupling. So when you control the temperature, you do not directly control the velocity field. You control only the forcing. So it is non-trivial to ask whether, if we have the same forcing everywhere, will we have the same velocity field everywhere? This is not. It's not something that we can state trivially. And so the kind of the broader idea behind this is, firstly, to have this kind of a data extraction and try to extrapolate it to regions where we do not have data. And eventually, maybe the idea is that once we understand which regions or which regimes or how they react to this nudging and our data inputs, maybe we can get smart, or maybe our algorithms can be smart, and we can learn from this and try to go to the next step. Instead of asking a flow to follow some other flow, we can ask a flow to do what we want, or at least move it, push it in a direction that we wish for it to behave like. So this is just a broader idea. So now we have just a quick note of the setup. We start with a zero velocity everywhere, and we initialize the temperature to the correct temperature where we nudge, which is around in these L-sized boxes around the particles. And I want to say here that we have a no flux boundary for temperature at the top and bottom walls, which is different from, so we are not driving the flow, because otherwise, since this is a thermally driven flow, if we even set the temperature at the boundaries correctly, then I think it would be giving a lot of information to the flow. Hence, reconstruction would not be so impressive if we are able to do. And so we evolved the dynamic equations, and we make these measurements once the flow attains a stationary state. So initially we have zero velocity, and then the energy increases, and then it attains a stationary kinetic energy. And we use the lattice Boltzmann method, the D2Q9, with two populations. So for us, we have these two flows with a lower Rayleigh number and a higher Rayleigh number. We know that the transition to turbulence in this Rayleigh-Benard system happens between a Rayleigh number of 10 to the power of 7 to 10 to the power of 9. So we can say that this is moderately turbulent or slightly turbulent, while this is quite a turbulent flow. And we consider different nudging volume fractions, and we do a bilinear interpolation to obtain these off-grid temperatures, and linear interpolation to obtain this the temperatures measured by the probes. But I want to say here that our sampling frequency from these probes is really high. So basically, we are reading the correct temperature every time, because this is another complexity which maybe we can consider later, that what if we don't have exact measurements, or the data is corrupted somehow or something like this. So this is the first plot for some. This is the L squared error, the pointwise L squared error for the temperature field, and here what I call the nudging volume fraction in the x-axis is the number of probes multiplied by the L square, where L square is this box around each particle, divided by the total area. So I want to stress here that even though 25% sounds like a large number, it's a very significant fraction of the flow. I want to stress that when we look at the number of probes, actually, the true information that we are extracting to nudge 25% of the volume is still less than 1%, because the L we have here is 6. So this would, even with the 25%, we are nudging less than the information we extract is less than 1% of the total information. And we can see that this dynamic reconstruction is, once we have more data, we do perform better than a simple linear or a linear interpolation of the Eulerian, the Eulerian measurements or the Lagrangian measurements. Here we look at the reconstruction, that is the L squared error of the velocity field, which is what we really want to look at, because we haven't taken any data from the velocity field, but we can see that that we have a really good error, like reconstruction with a less than 10% errors for both the 10% and the 25% cases in the Lagrangian and the Eulerian regimes. And if we look at the Nusselt number, where the dark blue curve is the reference field, which is the original Nusselt number, we can see that, of course, at the boundary, we will be wrong, because in one case we have the zero flux, and in one case we have the correct, the Rayleigh-Benard boundary conditions. But we can see that in the bulk, for both the 10% and the 25% case in the Eulerian nudging, we do recover the Nusselt number quite accurately, and the same with the Lagrangian case. So, but these were the results with the flow with the lower Rayleigh number. When we go to the higher Rayleigh number, the reconstruction of the temperature field is more or less the same, because we are controlling the temperature. But if you look at the velocity reconstruction, I mean the L squared is quite a stringent test, and even with such a chaotic flow, I don't think we do too badly with less than around 40 to 50% errors. And but again, with the Nusselt number, we can see that even with just a 2% volume, we recover quite faithfully the Nusselt number. So this means, I would say that at a large scale level, at least, we are capturing something quite correctly. And you can see, again, to stress that even though our nudging volume fraction would be 25%, here the actual fraction of information, that is the number of probes divided by the total number of grid points, even in the highest case that we consider, is still of the order of 10 to the minus 3. So that's order of 0.5%. So, so I think with this, I conclude, and I would say that it's an initial study into this kind of thing, but I think there is still it's quite, we can be quite optimistic, given that we are quite we do quite well when we look at these kind of Nusselt numbers, and given that we really are working with very small amounts of data, and we are when we have more data, we are better than just a linear interpolation. I think it can be it is promising, and we are looking we will explore further into this. So of course, perhaps the most obvious question to ask is, what about alpha? And it is, I think, since it is something we have complete control over, we can really explore this parameter and fine tune this. And as I already mentioned, what if we have some kind of corrupted data, and the eventual goal is to have is to impose our own will on the flow using these techniques. And I would like to thank the European Union's Horizon 2020 Research and Innovation Program for funding this project. And with this, I conclude my talk. Thank you.
Okay, thank you very much. Time for a question or two. I don't know if any question in the audience.
I've asked lots of questions, but if you already asked the stepping forward. It's a very nice talk, but one thing really confused me. So you mentioned that you do not set the wall temperatures.
Yep.
Which means that the heat sinks and sources are only your probes.
Yes, yes.
Which seems very unphysical, because so in the limit of alpha going to 0, you will never ever be able to get the right solution.
Yeah.
The driving will be wrong.
Yeah, I mean, when we have alpha equal to 0, there will simply be no energy input into the flow.
Exactly, but you would hope that you would be able to get something with a very small alpha, but that also won't work because the input will be all wrong. So that's why I'm confused that if you were to set the heat correctly at the boundaries, you might have a better chance of just using a very small forcing and recovering the right kind of behavior. That would be, I think that's what you would want, that you have a very small alpha and still recover the right flow.
Yes, yes. This is this is an interesting idea, but I think from a kind of philosophical point of view, if we have the right temperature, then I mean we kind of know everything. We felt that it was more interesting to ask, without having the temperature, can we still reconstruct the bulb? But indeed, it could be a good exercise, an interesting exercise, to see if a very small alpha with the right wall temperatures could give a far better reconstruction, maybe.
Mm-hmm.
Okay, is there any other question? Okay, so if it's not the case, thanks again for this interesting talk, and we will move to the next speaker. So I'm a bit confused because I think you were the second speaker, and the first one, I don't know if it disappeared or it canceled. So I don't know if Dr. Schuh is around, or we move directly to the last talk, Dr. Trunk.
Hello, hi.
Hi.
Hi, I am the next speaker, Ugo.
I think you missed
you're the first one.
No, you mixed it up, Dr. Schupart. It's in the other session. It's not in this session, in the other. Yeah.
Okay, so there is a change of program. So whoever is supposed to speak now, please.
Yes, I think according to the program, I should speak in the virtual room, Leone, after Lockhart, as I understand.
Okay, so for me, we are session 13, and Dr. Agasthya was second, and now there's Dr. Trunk. I don't know if the program changed, so, but I don't know.
Okay, but
So, I mean, if the only one who are claiming to speak now, you should speak.
Okay. So I think I will speak. This is what I understood by the program.
But you probably have another version than I have. Important is that the speaker is around.
Okay.
So,
Let me.
floor is yours.
Is it possible to see?
Yeah, we see your screen and we hear you. So I guess you have 20 minutes, including question.
Okay, so thank you. I would like to thank you for the opportunity to be here. I'm really glad. And this is a work in collaboration with Luca Biferale and Mauro Sbragaglia from the University of Rome Tor Vergata, and also in collaboration with Alexei Mailybaev, my advisor in the Institute for Pure and Applied Mathematics in Rio de Janeiro. So here I'm going to talk about, especially about two-dimensional immiscible Helitalo turbulence. And we simulated this phenomenon using multi-component lattice Boltzmann models. And because we want to test a series of phenomenological predictions, especially for the immiscible case. These phenomenological predictions are related essentially to, in a first part, to mixing layer, typical velocity, average density profiles, and entropy. And we compare these predictions side by side with the immiscible case. And in addition, we also build some, we also show some statistics only related to the immiscible case, which is the case of typical drop size and total length of the interface. So what is this Helitalo phenomenon? What is this Helitalo instability? It happens when you have two fluids with different densities separated with an interface, and you imagine a configuration when you have a heavier fluid placed above the lighter one, the lighter fluid. And this is an unstable configuration, and when you disturb the interface, sometimes happens the interpenetration of the materials of the fluids, originating this picture for the miscible situation, and this picture for the immiscible situation. This is, I believe, it's something relatively new with this level of details. The immiscible case is something well known in the literature. So how we simulate that? We use the classical Shen multi-component method, which simulates fluids using a connection between classical Boltzmann equations and hydrodynamic equations, a connection made by the Chapman expansion. So here we use the Shen force scheme with the Shen force in term, which considers that the interaction between components is proportional to the density, the product of the density in every point, and the intensity of the attraction or repulsion is connected to, is associated to this parameter GAB. And also the parameter GAB regulates the miscibility and immiscibility conditions. Okay, so in the Shen multi-component model, if you using an appropriate external force scheme, you can obtain the Boussinesq approximation for the system. And you have compressibility condition, Cahn-Hilliard equation, and Navier-Stokes equation with generalized pressure tensor, including the Korteweg stresses, responsible for surface tension in the immiscible case. So here we have a video of the immiscible case. I also have a video for the immiscible case if there is anybody interested. But I think what is interesting about the immiscible case, despite the simplicity of the lattice Boltzmann method used, there are several issues related to appropriate simulation of this phenomenon. And some of the issues are related to the long time necessary to simulate the phenomenon, the large computational fluid domains, the high Reynolds number required, and all of these requires a very delicate adjustment of parameters, and an appropriate treatment of the initial conditions. So in the literature, you see a lot of reference to the miscible case, but a very few for the immiscible case. And most of them are related with the early stages of the simulation. And it's even harder to find verifications of phenomenological predictions. Okay. So in most part of the phenomenology is dedicated to the miscible and immiscible Helitalo. A very important measurement is the mixing layer length. So here we define the mixing layer. This is our definition as when when both components reach 20% of the total density. And you see that there is a cutoff region, a region we cut to avoid the effects of the non-homogeneous part of the mixing region. And also, once you have a definition of the mixing layer, it's also possible to define a notion of typical velocity using the mean square root of the velocity intensity in the mixing layer region. So, okay, a very quick phenomenological prediction can be obtained through simple dimensional analysis in the Boltzmann system, when you compare the time derivative in the left-hand side with the buoyancy term in the right-hand side. And you obtain that, the conclusion is that for late times, the mixing layer should grow quadratically in time, and the typical velocity should grow linearly in time. Numerically, we try to verify the alpha coefficients. If you see that it's possible to have a well-defined alpha coefficient, so we have a verification of these predictions. This is the pure measurements, and we see in the picture A, measurements for mixing layer, miscible and immiscible. Picture B, measurements for typical velocity, miscible and immiscible, and the measurements of the alpha coefficients for miscible and immiscible. And in picture A, alpha coefficient for miscible layer, and picture B, alpha coefficient for typical velocity. And we see a relatively good agreement, and also not a significant difference between miscible and immiscible. Another important measurement for to check the phenomenologies is the horizontally average density profile. So you take the horizontal average for the density profile, and you find a function of the vertical coordinate. So we take this function for 3 consecutive times in the times corresponding to this flat region observed in the graph of the mixing layer. We argue that this flat region corresponds to the fully developed Helitalo turbulence. So we see that the density profile shows a linear shape, which indicates statistical homogeneity inside the mixing layer. And also it has an inclination decreasing like T2 minus 2, as predicted. So we have a good agreement with the phenomenology. And also, we don't see a significant difference between miscible and immiscible. So now we're going to address what we saw, which is the biggest difference between miscible and immiscible, which is related to the small scales and the statistics. So if assuming in the 2 dimensions, assuming the Bojano-Obukhov scenario, you have a turbulent picture where you have an initial range limited above by the mixing layer length and below by the Kolmogorov scale. In this initial range, assuming the Bojano-Obukhov scenario, where you assume that the energy flux due to the nonlinear terms is balanced by the energy flux to the buoyancy term, you obtain a series of phenomenological predictions for velocity fluctuations or the parameter fluctuations and the evolution of the Kolmogorov scale. And also, using the same assumptions for the immiscible case, you can obtain statistics for the typical drop size of the system, looking for the scale where the kinetic energy density and the interface energy density are the same order. And we extended this phenomenology to provide an estimate of the total length of the interface. Actually, this estimate is a upper bound for the interface, and we're going to check some of these phenomenological claims. Similarly, using a very simple dimensional analysis argument, we provide a phenomenological prediction for the typical size associated with structures with different size than the typical drop size. And you see that the total length associated with these structures scales linearly with the curvature. So, numerically, in terms of numerical experiments, so to investigate the statistics about typical drop size, first we extended the notion of typical drop size to investigate what is the most typical curvature radius of the system. For example, in the picture A, we have a picture, part of the interface. And for every point of the interface, you can imagine the interface as a big polygonal line with many components. And for every point of the interface, you can associate a curvature, taking the 3 adjacent points. And for every point, you can also associate a length, taking the average of the length of the adjacent line segments to this point. So, in conclusion, for every point, you can associate a curvature and a length. And with this information, you can build an histogram with length frequencies. And this histogram has a well-defined maximum. So this maximum shows what is the typical curvature radius of the system. So analyzing the evolution of this maximum in time, we have a phenomenological, we have a numerical verification for the prediction of typical drop size. So we have a relatively good agreement between our measurements and the phenomenological predictions shown in picture C, the evolution of typical drop size. And also in the picture B, we also have a very good agreement between the phenomenological prediction that the typical size associated with structures with curvature radius different from the typical curvature scales linearly with the curvature, or is related to the inverse of the curvature radius, as shown in picture B. So this is a very good agreement with our phenomenological prediction. So the total length, we also calculated the total length using a classical formula from differential geometry called Cauchy-Coffstrom formula, which measures the total length of the interface, counting the number of intersections with families of straight lines. And it's a very accurate formula, and also stable and easy to implement. And in the picture E, we have the logarithmic derivative showing what is the power law of the system, the tendency to the power law. The phenomenological prediction obtained by us is indicated by the solid black line. And remembering that our phenomenological prediction is an upper bound. But despite to be an upper bound, we see that is still very close to the real exponent of the interface, which grows with something like 1.664. Okay. In a very simple way, it's also possible to obtain an estimate for the entropy. And the estimate for the entropy shows that the entropy should grow with the power 3/2. And in this picture, we see a verification of these phenomenological predictions. We see a surprisingly good agreement in the immiscible case. And we also investigated the statistics of the entropy far from the interface. And to do this, we investigated the entropy with interface and the entropy cutting a region around the interface, a significant region around the interface, and the results is showed by this immiscible filtered curve, the dashed curve. So it shows that the statistics of entropy far from the interface still verifies the phenomenological predictions. And this is a picture of the vorticity field. I bring back some of the pictures from the beginning of the presentation, and I calculated the vorticity field associated. We can see that the high vorticity, the vorticity with a high intensity in the immiscible case, is it's close to the interface. And we also see by the difference in the limits of the color bars that the typical high vorticity in the immiscible case is twice as bigger than the vorticity in the immiscible case. And a measurement of this difference can be seen in this histogram. So in blue, we have the histogram for the vorticity field for the immiscible case, in red for the immiscible case, and the dashed line represents the histogram for the far from the interface, when you exclude a region around the interface. We see that when you exclude a layer around the interface and a region around the interface, you see that the main difference happens in the high-intensity vorticity, the vorticity with high intensity.
So 5 minutes. Huh?
Okay, so this is what essentially what we have done, and so we managed to simulate properly the fully developed miscible Helitalo turbulence. It seems that there is not a significant difference in large-scale statistics, and the interface seems to affect only the small-scale statistics, as we see in the measurements of the entropy, and we see a good agreement. We see that the numerical results for the interface have a good agreement with our phenomenological predictions. And I would like to thank you for the attention, and I'll be happy to hear your questions.
Okay, we have time for question if any in the audience.
Hugo, that's a very nice talk. Thank you for that.
Thank you.
If I understood this right, the assumption here is that these two fluids are entirely symmetrical, right? But of course, if you have real fluids, presumably they'll have.
Could you repeat?
Yeah, so your two fluids are basically have the same kind of, say, heat capacity, heat diffusion coefficients, and things like that,
yes,
right?
Yes.
But you could well imagine that quite interesting things could happen, particularly in the immiscible case, if these properties were different. For instance, if one of your two fluids has a much higher heat capacity, right? Or
yes, I suppose.
Heat diffusion coefficients or heat conduction ability was very different for the two fluids. Then you would get very asymmetric results, presumably, which would change the results a lot. But that's probably of significance for many of the practical applications where the two fluids are going to be quite different.
Yes, I suppose. I think this is what I've done here is a first approach to the problem. I think to the best of my knowledge, I didn't see any reference showing this fully developed immiscible with such details and with measurements allowing phenomenological verifications. But I think that a good direction for the future would be to change an asymmetric system, I think.
Yeah, I think that'll be interesting stuff. We did some stuff quite a while back on when you do this around the critical point. So where you have miscible stuff turning into immiscible one in different parts of the temperature, and then you get sort of periodic drop formation and stuff like that. But that's a different kind of problem.
Ah, very, very interesting. Very interesting.
Okay. Any other question?
Very much.
Yeah, thank you. Thank you.
Okay. Any question from the Go? Okay, so if it's not the case, thanks very much, Hugo, for this.
Thank you very much.
So according to the program that I updated now, I think it's the end of this session. And I'd like to thank you all for attending. And I wish you a nice continuation wherever you go for the next steps of the meeting. Okay, bye-bye.
Okay, thank you. Thank you. Bye-bye.
Bye.